So I've had a few requests for a quiz. This which is surprising, right? Normally I will trust the quiz on you guys, but there is a second midterm that is coming up next week, next Thursday. Okay, so kind of a preview to that. This Thursday, that is the next lecture, I will have about half an hour quiz towards the end of the class. So I will take about 50 minutes of lecture, and then from 10 o'clock to about 10:30 or so, I will have a quiz. Remember, the quizzes always count towards the assignment. It will be treated as equivalent to an assignment. And it will be a preview of the type of questions that you should study for your second midterm exam next week. Okay? And the midterm exam will include everything that we cover till the end of this week. Okay, that is a little bit of functional approximation as well.
There's going to be a preview to the quiz.
Review to the...
Will it be posted with what we should be kind of looking at? Or
Well, I'll probably briefly tell you what you should be looking at. I feel that majority of you are now getting reasonably comfortable with MATLAB. Okay, that learning process is, of course, a lifelong, continuous learning process. I'm learning a lot about MATLAB myself in teaching this course. That is the status that you should get. That you should feel comfortable to learn more about it on your own. So I'm not going to place a lot of emphasis on MATLAB. There will be small section, maybe about 30% or so on MATLAB. Those will be not simple quiz or midterm type 1 questions where what will MATLAB produce. But I will have a little bit of functions, calling functions, and global and local variables, because I think some of you, when I look at the bugs, the kind of problems that some of you are encountering, maybe strengthening that part would be useful. So there will be a section up to maybe 30% weight on those kind of MATLAB questions. And the remaining, there will be a significant percentage on algorithms. That's the new topic that we have seen since the last midterm. What do I mean by algorithms? I mean, you should be able to describe in words what does the bisection method do? What do we mean by truncation error? What do we mean by round-off error? Okay, how do we control these errors? And what is rate of convergence? Okay, what is the rate of convergence of the Newton method? And what is fixed point iteration? Okay, so you should be able to read those sections and answer briefly for those kinds of conceptual questions. Okay, so that you have some idea of how these algorithms work. What is curve fitting? What is functional approximation? And how do you convert the functional approximation problem into a problem of solving set of linear equations, which is what we saw in the last class. And I felt that there was a little bit of discomfort there, so I'm going to review that again today. But those are the type of questions that will fill the second 1/3. So 1/3 on MATLAB, 1/3 on algorithm, 1/3 on problems. What type of problems? The problems that you have been doing in the assignments. I think the most valuable experience that you will get from this course is in doing those assignments, because these are substantive problems. Okay, you will see them in later on in individual courses when you do. But the flash problem, for example, is a very significant problem, and you are learning how to solve with HYSYS, how to solve with MATLAB, and what does bubble point mean, what does dew point mean. So a little bit of understanding the nature of the problem. Is it, for example, in the flash, two drums, that would be called a sequential problem, because you're solving the first stage and then you're feeding it into the second stage. Slowly we will build up where there is a recycle, because a typical chemical plant will have hundreds of such units, and there will be recycle, there will be feedback, and you should understand these concepts. So modeling, mathematical modeling will be the last third. Okay, MATLAB 1/3, algorithms 1/3, mathematical modeling 1/3. Does that answer your question? What to expect?
Yeah.
You will find that helpful, yes. You will find the actual problems, I guess, as a preview to exam in the quiz. Okay? So review those. And I'm not planning on conducting actual review for the midterm the second midterm. So the quiz will be the preview. Any other questions or comments? Okay. In the last class, we did introduce quite a number of concepts, and we formulated this problem of what do we mean by a functional approximation. Given a function f of x, find an approximation to that function. One way is a series expansion. So we saw an example of an error function. So it's an infinite series. I can truncate it, chop off, and then we have to deal with issues of what is the error in making that approximation. How do I take charge? How do I control that error? Okay. So the larger the value of x, the argument, the more terms than I need in the series. Okay. And then we saw, given a set of data points, find a functional approximation for it. I'm going to do a more detailed example of that. And why do we need functional approximation? For interpolation, for extrapolation, for numerical differentiation, and integration. You should know what interpolation and what extrapolations are. And then we introduce MuPad. MuPad is the symbolic processing toolbox in MATLAB, which allows you to take derivatives. For example, the Jacobian that you need to write, you could actually enter that expression in MuPad and ask MuPad to take the derivative of that expression with respect to psi. Okay? And then take that piece of code, cut it, and paste it into the Jacobian function. So today I'm going to introduce a little bit more about MATLAB. So far we've been talking about MATLAB programming. There are some nice features in MATLAB where MATLAB itself writes a program for you. So now I think all of you are convinced about how easy it is ISIS, right? To use ISIS. MATLAB is still a frustrating point. Now, whenever you do programming, you need to have some logical understanding of how the flow of information occurs from one function to another function, etc. But MATLAB graphical user interface allows you to capture a lot of the things that you do into programming automatically. So it writes the program for you. So I will introduce some parts of that. That will make the life a little bit easy for you. Okay. And of course, we also saw the idea of a basis function, a concept that you should be able to explain in a quiz or an exam. What is a basis function? How do we construct basis functions? What are the important properties of basis functions? Things like that. So all these you will find elaborated a little bit more in the notes that I have put on Moodle. You should download and read that particular chapter 4. So let's review what we did in the last class. So if you give me a set of data points or a function from which I can generate a set of data points. Okay. So the problem is always I have a table xi, fi. Okay. So going from point 1 to point 5 as an example, and I have the x values. How do I construct a function that represents that data as accurately as possible? Okay. So we said that we can take that as a polynomial approximation to the given function and write it in terms of summation of ai phi I. Phi I can be any set of basis functions, and there are a variety of basis functions available, but in this course we are going to basically restrict ourselves to polynomial expressions. So the basis function is going to be simply 1, x squared, x cubed, etc. One of the important properties of basis function should be they should be linearly independent. What does that mean? None of the functions should be able to be expressible by others. For example, if the basis function x cubed in the series 1, x squared, x cubed cannot be represented as a linear combination of 1, x and x squared. X cubed is independent from the previous set. So that's how we expand our set of basis functions to capture more and more complicated data. Okay, so if I make that choice for my basis function phi I as x to the power I minus 1, I going from 1 to n, then the polynomial approximation of degree n minus 1 can be written as ai x to the power I minus 1. So all I have done here is I made a choice for the basis function that I have there. So I'm going from step 1 to step 2, I made a very specific choice for the basis function. Okay? And we went through this last lecture, but I just want to make sure because I felt uncomfortable that I saw a lot of blank faces. Okay? So let's take this problem of error function. I want to approximate the error function in the range from point 1 to point 5. Error function is defined from 0 to infinity. but I'm taking only one section of it, 0.1 to 0.5, and I've chosen to approximate that section of the error function from 0.1 to 0.5 using 4 terms. These are the choices that I make or you will make when you're doing a curve fitting. Okay? So when I say, I think the problem is when I present it in terms of general n and index notations with indices everywhere, you have a problem in grasping it. So hopefully a specific example will illustrate that, but you should be able to program the general expressions in MATLAB. Okay? That's how you write generic functions. So for n equal to 4, that means my basis function consists of 1, x, x squared, and x cubed, because I'm taking 4 functions. So n is 4, so the last term will be only x cubed, because it is x to the power n minus 1, or I minus 1, as you see here. Okay? So with that one, my third degree polynomial can be expanded. That is, now I'm taking this equation and expanding it for a very specific case, n equal to 4. So the third degree polynomial, n is 4, so Pn minus 1, which is P3, equals a1 plus a2x plus a3x squared plus a4x cubed. That is a polynomial expression that I want to use to capture the error function in the range from 0.1 to 0.5. So in this expression, x can take any value between 0.1 and 0.5. In fact, it can take any value from minus infinity to plus infinity. Okay? Because x is the independent variable in this expression. Okay? And P3 is an approximation to the y, or the error function. The unknown coefficients are a1, a2, a3, a4. I don't know what they are. But what I want to do is I want to pick the best possible values for a1, a2, a3, and a4 such that this polynomial representation is the best possible representation for the error function over that range, 0.1 to 0.5. Okay? That's my task. So I need to have 4 conditions because I have 4 unknowns. A1, A2, A3, A4 are unknowns, and in order to solve for them, I need 4 conditions. And these 4 conditions, I'm going to say that polynomial and that error function must be exactly the same at 4 data points in that range from 0.1 to 0.5. So what I'm going to do is, graphically, this is x-axis, this is 0.1, and this is 0.5. And I'm going to take 2 more points in between, equally spaced. And at those points, I have the values for error functions. It may be like this. So I want my curve that I'm going to draw to pass through exactly those points. So at those points, the error between what I predict from the polynomial and what is given from the error function should be 0. Okay? I've already defined the error as the difference between the error function. This, in fact, is applicable for any function. F of x could be any function. In this example, I'm taking error function. And the polynomial. Okay? The error between those two must be 0. Okay? So this is not least squares. This is exactly forcing the polynomial to pass through those 4 points. Any questions on that? Conceptually, you're all okay with me? Understanding what we are laying out? What we are going to do in numerical analysis, you will find that any problem like this is eventually converted to a problem of solving a system of linear equations, linear algebraic equations. Now, I've identified A1, A2, A3, A4 as unknowns, okay? And I've identified my range, x, from 0.1 to 0.5. So the next thing I need to do is identify where those points are. So I'm giving you the formula in general terms. The formula is going to be such that it starts at A, ends at B, and has equally spaced data points between, depending on the choice for n that I make. Okay? And those points will be labeled as x1 equal to A, x2, x3, and then xn equal to B at the other end. In this particular example, I'm going to choose 2 intermediate points. And then I said I want the error at those points. So xk here stands for those so-called collocation points, the points where I want the error to be equal. So I evaluate that function at xk. So now this becomes a known number because it is the error function evaluated at those 4 data points. Okay? And the polynomial must also be evaluated at the same points. And I want the difference between them to be equal to 0. Okay? I'm forcing the error to be equal to 0. So when I substitute for the polynomial expression is this, and f of xk goes to the right hand side. So I have a set of linear equations n equations, k equals 1 to n, and that are captured by this particular expression. Aix k to the power I minus 1 equals f of xk. Your job in an exam would be, I identify instead of error function some other complicated function. I say instead of polynomial, use some other expression. Your job would be to formulate an expression like this and write it in this form. That is, you have to, that equation you should recognize, but at the end of this course, that should be second nature to you. If I give you an equation like this, and I tell you that A1, A2, A3 are the unknowns, that can be written as a matrix P multiplied by a vector A equal to the function F vector on the right hand side. Now this is known, and all the elements in P are known. So you should be able to assemble those. Okay, and that's what we're going to go through specifically for the 4x4 example. But everything that I have said here is generic for any function, any polynomial approximation basis set, using the degree of freedom that you have identified to formulate this problem. Any questions on that part so far? Now, MATLAB simplifies all these jobs for you because MATLAB can code all the algorithms. So I will show you something called CF tool, curve fitting tools, which has a graphical user interface, and we will do steam table, curve fitting, etc. with that. Okay. So we want to understand the theory behind it. We want to be able to learn how to do it, and then learn what tools are available in MATLAB. And if you look at HYSYS requires all these properties. Okay, it needs the vapor pressure, it needs the viscosity, surface tension, etc. All these are available in specific databases, and these databases are extracted from experimental data, curve fitting sometimes using equations of state, etc. So that part of HYSYS is where functional approximation will be used most extensively. Okay, so that's going to go back to that problem with 4 equations in 4 unknowns. So n is equal to 4 in this case, and I want this error to be equal to 0. I said I need to pick 4 points, right? The left point is point 1, the right point is point 5, so I need to pick 2 points in between that are equally spaced. Okay, so starting at point 1 and point 5, what I need to do is find what is the range. Point 5 minus point 1 is point 4. I want to divide that into 3 equal intervals. Why 3? Because I need 4 data points. So here are the 4 data points, and that gives you 3 equal intervals. So I divide it by 3. Okay, so 0.4 divided by 3, this is 0.1333. Okay, that is the interval. So what should be x2? x2 is this. x1 is this. x2 should be 0.1 plus 0.1333. So that gives you 0.2333. This is simply the application of the general formula that we gave here. Okay, how to divide between 2 points starting at A and B into equal intervals when we make a choice for n, whether n is 4 or 5, whatever. That formula will give you those equally spaced points. Okay, then x3 is going to be 0.233 plus the next delta x, which is again 0.133. So that gives you 0.3666. And you add another 0.133, that will give you 0.49999. I'm saying that is 0.5. So remember, what is round off error in computers? I asked you to be able to ready to explain that, yeah? Pardon me, say it again.
The round off error is like just what you specify the tolerance.
No. The tolerance is something that you control. The round off error in a computer is something that you cannot control. It is determined by the architecture of the CPU, okay, and the algorithm that are used to exploit that. Round off error is the error that you introduce in rounding off the last digit. 1 over 3, for example. What is the representation in decimal representation of 1 over 3? 0.33333 forever to infinite digits. But MATLAB and most computers cannot carry more than 16 digits. Okay, so there is a rounding off from the 17th digit to 16th digit, and MATLAB will apply or the CPU architecture will apply an algorithm for rounding that off. The error introduced by that is called a round off error. And round off errors will always be there in any computer. Now, the tolerance is something that you can choose. You can say, I don't want 16 digits, I want only 4 digits. Then you can specify the tolerance, and you will get an answer only to 4 significant digits, because you deem it to be converged once you get 4 digits accuracy. Okay? So it is related to the round-off error. The maximum tolerance that you can specify is determined by the round-off error. But round-off error is the process by which computers use infinite precision to a finite precision. Okay? Now, symbolic toolboxes like MuPad can give you values and carry the arithmetic to extended precision, but it does it using special algorithms. But by default, most of the calculations in MATLAB are done to double precision, meaning about 16 significant digits. So these are round-off errors, 0.2333. It actually should go along, but I'm truncating it to 4 decimal places. So the best answer I could get is only about 4 significant digits, unless I extend this to 16 significant digits. But if I extend to 32 significant digits, it doesn't improve the accuracy, because MATLAB will then come and say, I'm truncating it after 16. That is the round-off error. Okay? So at collocation point 1, there is a first point. This is the most important part that you need to understand. What does this equation mean? Okay? That equation I'm going to apply for k equal to 1 to get the first equation, then k equal to 2 to get the second equation, k equal to 3, and k equal to 4. That's how I get 4 equations. I have 4 unknowns, A1, A2, A3, A4. These are the 4 degrees of freedom. Okay? So A1, all you have to do is put k equal to 1 and expand the left-hand side. Left-hand side is a summation over I. So I is going to be equal to 1, 2, 3, 4. Okay? When you put I equal to 1 and k equal to 1, you will get A1 times x1 to the power 0. Anything to the power 0 is 1. Okay? So that's simply A1. Plus A2 when I is equal to 2 times k is still 1, because I'm dealing with, in this equation, always k is equal to 1. I'm dealing with the first equation. Okay? So the second term is I is equal to 2. The third term is I equal to 3. The fourth term is I equal to 4. That's how you would expand that. So when you expand that, you will see A1 plus A2 x1. x1 is a known number, because I know what x1 is. I can plug it in and I'll get a number out of it. The unknowns are A1, A2, A3, A4. Okay? And x1 square, I can square it. x1 cube, I can cube it. On the right hand side, I can find the error function at x1, which is a number that is also known. So the next stage, I'm substituting actually the actual values, and I get a linear equation in the unknown A1, A2, A3, A4. That is my first equation, k equal to 1. Is it any better than last lecture? Do you understand the process? Okay? Then you repeat the process. Now k is equal to 2. Okay? So this is going to be x2. x2 cube. And this is the function is evaluated at x2. Still you have, yeah, sorry.
Is there a typo, or is it supposed to be an A4 after or before the 0.001?
It is a typo. Thank you. Now, when a question like that comes, I feel that you understand it, right? You put this is not a deliberate error. Sometimes I do plant errors to see whether you can catch that. But that is a typo, so I should have A4 here. Okay? And that's it. So if you understand that, you know how to get all the 4 equations. Now the problem, if you do it by hand, is it's tedious. Whereas if you can get the general formula and program it, you can do polynomial curve fitting of any degree. Okay? And that's the advantage of writing a program using the generic formulas instead of the specific ones, but doing it by hand once helps you understand the process. Okay? So now you have the 4 equations. All you have to do is put them in a vector matrix form. Remember, I wanted you to write it as P times A equals F. Okay, so let's do that. Okay, so here I'm going to put A1, A2, A3, A4. On the right hand side, I need to put the first function, which is 0.1125 from the first equation. And then I have 0.2583. And then I have 0.3959. And then I have 0.5205. These are the 4 function values for the error function at those 4 collocation points. Okay, what will be on the left hand side? The matrix P. 1, 0.1, 0.01, and 001. Now you can see if I take more terms in this, what would happen? The next term would be, if I have a 5 by 5 system, for example, 3.0001, something like that. So the matrix is not well scaled. All the terms are not of the same order of unity. This causes the matrix to be singular, meaning its determinant is going to go to 0 very rapidly. So it's very difficult to invert that. So the error in the polynomial coefficients will be very large. So you never fit a set of data points to very high degree polynomial. Okay, you always choose a lower degree polynomial. Everybody understand how the matrix is assembled? And also understand why the matrix becomes poorly scaled. Because it will always be very large variation in the magnitude of the terms in the matrix. And so its inverse is becoming very difficult. So the next row, this is for k equal to 1. You will put k equal to 2 here. And the next row would be 1 again, and then 0.233, 0.233 square, 0.233 cube, etc. Now you get the idea. Okay, that's how you would assemble it, and you should be able to do it in a program, not in an exam. You should be able to do this, what I've shown you exactly, by hand, fill the matrix. Okay, but in an assignment, you should be able to program it in a more generic fashion. And that's all curve fitting is. Curve fitting exercise is just that. Okay, converting the problem. You're making a choice about the basis function, and then you're converting the problem into a problem of solving a set of linear equations. Now, what I've shown here, this is a result generated in MATLAB using 5 points. Okay, so you can see those 5 points, 1, 2, 3, 4, 5. This is from the error function. The blue line that you see here is the error function. I've chosen x to be in the range of 0 to 3, but in fitting the polynomial, I've chosen it from 0.1 to 0.5. I've taken 5 points from the error function in that range, and I have fitted a polynomial of the fourth power, fourth degree polynomial. In a fourth degree polynomial, how many unknowns will I have? 5. Okay, because the last, the P4 will be written as A1 plus A2x plus A3 x squared plus A4 x cubed plus A5 x to the power 4. The degree of the polynomial is determined by the highest power. So if I have a fourth power, that means I'm going to have 5 coefficients in there. That's why I need 5 data points. So I've taken the 5 data points in the range from 0.1 to 0.5, and then I can evaluate that polynomial over the entire range 0 to 3. And when I evaluate the polynomial, this is the fitted polynomial. What do you see in this? Very good. Does everybody see that? What I wanted to make, the point I wanted to make with this graph is, if you are using a certain range from 0.1 to 0.5, in that range you can have a very good representation of the error function, because the error function falls on those 5 data points very well, because we forced it to go through those 5 points. But as you go outside of the range, that polynomial becomes a very poor representation of the error function. Error function is bounded, goes to 1 as x goes to infinity. But this polynomial, which is supposed to be an approximation to the error function, just blows up, diverges, goes away. And this range would be called extrapolation. You never extrapolate outside of the data points very far away. That is one of the problems in packages like HYSYS, because they might have fitted a viscosity data, for example, for water over a range of temperature from 60 to 100. Now you may accidentally evaluate it 150, in which case it may not even be in the liquid form if the pressure is atmospheric pressure. Okay, so you could, during the iterative process, when you are making a guess, you could go outside of the range. When that happens, that formula provides incorrect results and causes the HYSYS to diverge. So those are the problems one has to be aware of. When you are doing curve-fitted data, you should never extrapolate far outside of the range. Interpolation will always work. Question?
When looking at it, I mean, like obviously when it goes from one, it's still kind of along the curve on the x-axis or whatever. How would you know, like, in a situation that was how far past the range
you would not know a priori. That is the unfortunate thing.
Would you suggest, like, just kind of don't go past the range, or?
Don't go outside of the range, maybe 20% on either side. And you always be aware to check whether the state of that particular equation is valid in those ranges. So they should always give you what is the range over which that particular formula is applicable. Okay. Now, there is an excellent database of physical properties maintained by National Institute for Standards and Testing, NIST. And they have a website called ChemWeb. So you can extract almost any properties, including bubble point, dew point, etc., through a web-based interface. And it is very well done because every correlation that they use, they will tell you what is the source, where did they take that data from, experimental data or model, and what is the range of applicability for every temperature, pressure, whatever that independent variable is. So that would be kind of your reference material if you're looking at problems of this type. But never extrapolate, understand what interpolation is and what extrapolation is. Interpolation is if I ask you to calculate what is the error function at a value of 0.35, we had the data at 0.1, 0.2, 0.3, 0.4, 0.5 for this particular case. 0.35 would be an interpolation problem because you don't have the data, table of data. You have it at 0.3 and you have it at 0.4. And I'm asking you to calculate it at 0.35. Okay? Using the fitted green curve. And that will give you an answer that is pretty close to what you have from the error function. But if I say calculate the error function at 2.5, the error function at 2.5 is this, but you're going to predict this by using the fitted formula. Okay, yeah?
In this case, we use like x squared, x cubed for basis functions. How are we going to know when to use something else like suppose like log or sine?
That is a good question. There is no unique answer to it, but there are, when you go for higher math course, you will see that there are Fourier series is one that we talked about, cosines and cosines. Those are well bounded between 0 and 1. So polynomial expressions like x to the power 3, x to the power 4, they just blow up to infinity. Whereas sine, for example, is bounded no matter how large x is. It is always bounded between 0 and 1. Okay? So there are a lot of functions like that. Fourier series is one example. Then there are others called Chebyshev polynomials, Legendre polynomials. These are the basis functions that you would use in solving differential equations, as well as in some curve fitting data, you could use that.
Also, if it's less linear and on parts of the curve, and you have more curvature to it, would you need more points or would it still?
That is, again, a very good question. If the data has a sharp gradient in certain region, you have to ask the question, where did I get the data from? If it is coming from an experiment, I should sample more data points in that region. Okay? Or if it is coming from an expression like an error function, you evaluate the function at more data points. So putting more data points will increase the accuracy of an interpolation formula. But we will see soon, don't fit a very high degree polynomial, because high degree polynomials have this kind of a feature, that they will blow up, they will oscillate wildly. And so use a lower degree polynomial, but use something called least squares fitting. So we'll see what least squares fitting is later on. Okay, that will smooth out the errors, minimize the errors even from experimental data. It's a good question. Any other questions? Okay, so from this graph you should know what is interpolation, what is extrapolation. That extrapolation is not a very good idea always. Okay, so here I've just given you the same kind of example that we went through for a fourth degree polynomial with 5 data points, which shows that you have x5 to the power 4. Whenever you have that, you will have 4 scaling. Question? Yes. I always give you the difficult part and then the easy part later on, right? The reason is if you use only the easy part, you don't understand the theory behind it. Okay? It is very important that you have some idea of how does polyfit work. Somebody asks you, how does polyfit do? It does this process. It automates this process for you. Okay? So there is something called polyfit and there is something called polyval. Polyval evaluates the polynomial. Polyfit, what do you think polyfit will do? what will it return? What will it take as its input, and what will it return? It will take the x and y pair of data points as inputs, and it will return the coefficients of the polynomial. It will also take the degree of the polynomial. Okay? So here I'm going to go through polyfit and polyval for the next example. This example is a set of data points from steam tables. Okay? All of you are familiar with steam table, right? What does this data mean? I'm telling you that this is a data for the saturation data on steam table. So what do you think it would represent? T is the temperature, and it is a saturated mixture of water and steam that's in equilibrium. So that is the saturation pressure. Have you seen phase rule? Does the name phase rule ring a bell? P plus V equals C plus 2, something like this. In any phys chem or physics class. That comes from degree of freedom analysis too, which tells you, depending on how many phases and how many components, what is the degree of freedom. Okay? When steam and water are in equilibrium, you have two phases, P is equal to 2. And you have only one component, it's basically water. So C is equal to 1. Okay? So V is called the degree of freedom. It's exactly the degree of freedom analysis that we did. You will see that in a thermodynamics course. So Gibbs, yeah, Gibbs phase, that's right. Where did you see that? Okay, so you have seen it. Okay, so that tells you how many degrees of freedom that you have. So when you have water and steam in equilibrium, there is only one degree of freedom. V is called the degree of freedom, and V turns out to be 1. That means if I fix the temperature, the pressure is fixed. I don't have any control. Or if I fix the pressure, the temperature is fixed. So there is a unique data between temperature and pressure. That's what steam tables will list for you. I've taken a small subset of data from 220 to 232. The steam tables will have all the way from 32 degrees Fahrenheit or 0 degrees Celsius to 400, 500 degrees Celsius. Okay? What is the temperature, and each temperature, what is the saturation pressure? That is measured, and then it's tabulated in steam table. Okay? So, first question to you. Here is the data, and I want to capture this data in the form of an expression. Meaning, I want to express P as a function of T. I have only 1 degree of freedom, so if I give me temperature, I should be able to predict what the P is. So if I ask you, what is the saturation pressure at 224, it's very easy. All you have to do is read from there. But if I ask you the question, what is the pressure at 222, what will you do? Linear approximations. Very good. So you're already jumping into it. Interpolation. That problem would be an interpolation problem. Okay. If I ask you to evaluate it at 218, that would be an extrapolation problem because you're going to go outside of the range. Okay. So we will look at now using MATLAB tools to solve this problem and learn about how the curve fitting is done. Maybe we should do it with polyfit first and then with CF tool. So this is a new tool that I'm going to introduce called CF tool. It is curve fitting tool. Okay, question?
Which one specifies your degree of freedom? Is it V or C?
V is the degree of freedom.
And V is the number of phases?
P is the number of phases. P is the number of phases, and C is the number of components. Okay? Okay, so let's go into MATLAB and see how I extract. One of the things I think is there is a nice link between Excel and MATLAB. We can actually exchange data from Excel. Often these data may be given to you in the form of an Excel spreadsheet. So MATLAB has an interface that extracts this data into MATLAB from Excel. Okay, so here I have an Excel spreadsheet called steam tables, S for small data set and L for a large data set. Okay, so I'm going to open this up. All you have to do is, I'm going to do very little programming. Okay, and show also how to write program, how to ask MATLAB to write programs for us. Okay, so let me just double click on the steam table. It's an Excel file that appears in your folder, and you just open it up. And MATLAB will automatically recognize that it is an Excel file and attempt to read the contents of it and provide an interface through which you can import data from there. Okay, it opens up an import wizard, and it shows you a preview of the data contained in that Excel spreadsheet. So the spreadsheet contains only this data. Okay, so if there are column headers and stuff, they will also show you what they are. But I'm interested only in the data, so I'm going to extract the data. Okay, so I just say next, and then I say finish. And what it has done is it has extracted all the data from that Excel spreadsheet and put them in a variable called data. It automatically created that. Okay, so I'm going to double click on that. Remember, no programming. Okay, double clicking on that, and I see that there are two columns of data. The first one is the temperature, the second one is the pressure. So I click on number 1, and then right click, and I can say create a variable from the selection. So I'm going to call the first column temperature. But what it does is it automatically puts the first column into a new variable called unnamed. I haven't named it, right? So I click on that and rename it as T. Okay? Then go to the second column, right click again, and create the variable from the selection. And it creates another one called unnamed. I click on that to change its value to pressure. Okay, so from Excel, I have extracted two columns of data, pressure and temperature. Now I want to plot them. Okay, so I'm going to select these two. How do you select the two? Click on that with the shift pressed. So you can select multiple arrays like that. And then here I have a little icon called plot. Okay, so I select that, and it automatically gives me all the plots that I can generate using those two columns of data. Okay, so here, for example, it says plot P versus T. But I really want T versus P. I want T to be on the x-axis. So no programming, I just switch. Okay, and then I select by clicking on that. And it should produce a plot for me. Remember, see, look what happened at the bottom. It created the command that generates a plot for me. Okay? It created the command in the MATLAB window, and that is how the data looks. Okay, so on the x-axis I have temperature, on the y-axis I have pressure. I can go and embellish this graph any way I want. For example, I can just double click on where is it? Tools. No. Edit. Axis properties, for example. Okay, so that gives me, without programming again, ability to add anything that I want to the graph. Okay, so here I'm clicking on X label, temperature, degree C, and then y-axis, saturated pressure, ASIA, for example. Okay, so it immediately puts all those things, and I can put a title. Okay, steam table. So it automatically puts all those things. I can put a grid if I want. You can do whatever you want with changing this. But the important point is there is one menu that we haven't seen so far. It says generate code. Okay, so you do that, and it generates all the code that is necessary to create that graph with a different set of data points. So you are asking MATLAB to write the code for you. But what you should be able to do is, if you didn't know anything about MATLAB, this will all be Greek. You will not understand anything. But now you should be able to go and understand what it is trying to do. Okay? So it captures everything that you have done and writes a MATLAB function for you called create figure with two arguments, T1 and P1. Okay, so this whole template can be used, and you can pass new sets of T and P. For example, you want to plot the saturation temperature versus pressure, not for steam, but for methane. So you have a data from there, but you want the graph to look the same. you reuse this graph. So in every function that you do in MATLAB, you'll always have this thing, generate code. Okay, and when you use the generate code function, it writes the code capturing everything that you have done. Okay, it will look much more complicated than what we would have written because it does some fill-in generic scaling information and things like that. Okay, but it's a very powerful tool. Okay, any questions on that? All right. So now what do I want to do? I have created in my workspace a variable called t and a variable called p. Polyfit. So I want to use polyfit. So I'm going to call a equals polyfit t comma p. Comma, what should I, well, maybe I should ask help on polyfit to see whether how many input variables it needs and whether I can make any sense out of it. Okay. So polyfit, it says, takes 3 input arguments, x and y and n. What would n be? Can you guess? The degree of the polynomial, not necessarily the number of points, the degree of the polynomial. Okay. So we can choose a first degree, second degree, third degree, but with this particular data point, what is the largest degree that you could pick? Okay, how many data points did we have? I think we had 4, right? So the highest polynomial I can pick is 3. Then it gives me the 4 coefficients of those polynomials. Okay, now if I want to plot not only my original data point but the fitted polynomial, how would I do that? How would I do it? By command line? How would I do it from using the plot icon that you see on the right hand side here? You should be able to do both. Okay. Let me do it by command line. Plot t comma p comma. I'm putting symbols for the data points where I have t and p. And then I want you to help me now finish the next part of the curve. How would I generate a curve that uses the fitted polynomial? What is this coefficients? In the range of 220 to 232. Let's pick 210 to 240. So well, maybe I can calculate these separately. So I create a variable called xc, standing for calculated value, and I say I'm going to go from 210 in steps of 2 to 240. So all I'm doing is I'm picking the range of temperatures on the x-axis, going from 210 to 240, and I'm going to calculate yc, the calculated value of the pressure. How would I do that? I would use polyval in here. What would polyval take as an input? Can you guess? XC. Anything else? A. You need the coefficients of the polynomial, right? So you need to pass the coefficients of the polynomial, and you need to pass the XC, the range where you want to calculate that. So those are the pressures that are as calculated by the fitted polynomial. Now I want to plot this, t comma p comma this, comma xc comma yc, and I want that to be a line. Okay? Okay? Is it a good fit? It is a good fit because we are forcing it to go through those 4 points. Okay? So the error at those 4 points will be 0 because that is how we determine the coefficients of the polynomial. But outside of the range, we don't know whether it is a good fit or not. Okay? So the interpolation range will be from 220 to 232. Outside is an extrapolation, but the curve passes through those 4 points. Any questions on that? If not, I'm going to ask you this. Can I do this? If I do this, what will I get? I'm changing the order of the polynomial. Previously, I used the third degree polynomial, the same data set. Now I'm saying fit a first degree polynomial. It will give a straight line, but will the straight line pass through any of the data points? It cannot pass through any of the data points. Because if you are forcing it to pass through those data points, you must have 4 constraints. So you must have a third degree polynomial. If you have, how many degrees of freedom will you have in a first degree polynomial? How many coefficients will you have? A1 and A2. A1 plus A2x, right? So there are only 2 unknowns. You cannot determine those 2 unknowns by making the polynomial to pass through all the 4 data points. This is when polyfit automatically invokes a least squares approximation. Okay? So it will fit a first degree polynomial. It will give you these 2 coefficients. Now you can generate the data using the polyval with these new coefficients. That will give you a data that falls on a straight line. Then you can say plot that. Okay, so that is a straight line representation, the green line from the polyfit. And the data points are the blue circles. So the question to you is, if I calculate the difference between the fitted value and the actual value, will it be 0 or non-zero? At those 4 points. Am I getting the point across? Am I going fast in terms of? Yes, why? It could not pass through any of those data points. So there will be an error. Okay, maybe let's step back once and illustrate this a bit more slowly. So let me just take the 4th degree polynomial first. So here I have 4 coefficients. And I want to evaluate the polynomial predicted from this at those 4 locations. So I want to calculate the error. So I'm going to call error as, maybe you can help me. How would I calculate the error at those 4 data points between the predicted value and the calculated value? Absolute of P minus polyval A, comma, what are those 4 points? If you finish that, you're following me. How would I finish that particular sentence? P is the 4 pressure values that are in the table, that are imported from state table. Okay? Polyval takes the 3rd degree polynomial coefficient, and I want to evaluate at the same 4 temperatures for which the pressure is there. So what would I put there? Just T. Right? Those are the temperatures at which I want to evaluate those polynomials. What should I get out of this? What should be the number that I should get? Zeros? How many of you think it should return me 0 exactly? You are very close. But remember the round-off errors. It doesn't calculate to infinite precision. So it is 10 to the minus 13. Okay. So there are 0, 0, 0, 0, 13 zeros. So they agree, the predicted and the calculated value agrees to about 13 decimal places. Okay? And this is what we would call round-off error. This is due to round-off error. It should exactly be 0 if you calculated everything to infinite precision. Okay? But here we are seeing that it is close to 0. If I do the same thing with a linear polynomial, here I have generated a linear polynomial, and I'm using that to calculate the error. What should be the error? Should be as small as 10 to the minus 13? Will it be larger? It will be much larger. See? So a linear curve gives you 0.04, something of the order, second decimal place. Okay? So in general, the higher the order of the polynomial, the more accurate representation is at those data points, because you're forcing it to pass through those data points. Okay? But it has a disadvantage that you cannot extrapolate very far. Because higher degree polynomials, what do you know about the number of roots for a high degree polynomial? If I have a 10th degree polynomial, how many roots should I have? 10, right? So that means it has to cross the x-axis 10 times. Right? So it will have these high frequency fluctuations, higher degree polynomials. So in between, there will not be a good representation, even though it will pass through all those data points. So using a least squares is a better approach because it will not have these fluctuations. It will filter out all the high frequency noise in the data, the error in the data. So it's always better to strike a balance, not go for a very high degree polynomial, use a low degree polynomial, even though you have a lot of data, and use the least squares. But when you use the least squares, the error at those data points will be much higher than what you can get by exact fit. These are all important concepts that you should understand. I'm trying to illustrate it with a particular example. Any questions? Okay. So what do we know so far? We know how to extract data from a stream table from Excel into MATLAB, and how to do the curve fitting using polyfit and polyval. Okay. Now let's extract a larger set of data, because this small set of data actually looks very linear. It's not a bad approximation. The data itself looks linear because the range is small. I'm going to take exactly the same data, saturation temperature versus pressure, from a larger data set that I downloaded from the NIST website. Okay. In fact, let me go and open that website. If I can find it. Yeah, this is coming from Wikipedia. Yes, it can import data from a variety of sources, including just text file. If you have a flat text file in tables or something like that, you can import data from there. Yeah. Oh, I don't have the internet connection, so I cannot show you the Wikipedia where I took the data from, but I will put up this link so that you can look at the NIST database and what kind of data that they have. But I have already imported that data into this Excel spreadsheet. So the spreadsheet contains not only saturation temperature versus pressure, but it also contains other properties like the enthalpy of the liquid water and the latent heat of vaporization at those functions. So there are four columns of data here. First one is temperature in degrees C. The second one is the saturation pressure in kilopascals. The third one is the enthalpy of the liquid phase in joules per gram. And the last one is the latent heat of vaporization, all at these temperatures. So we have only 1 degree of freedom, the temperature. If you pick the temperature and say it is saturated water or saturated steam, then these properties are all fixed for you by the Gibbs phase rule. Okay? So what we need to do is import this data into MATLAB and do analysis on them. So let me clear this. And let me just double click on the large steam table. So now I want to introduce this CF tool, the curve fitting tool. Okay, and I guess one of the things I wanted to get from the website, maybe I should try to activate my internet connection. Okay, so here is the import wizard from within MATLAB, which accesses the Excel spreadsheet, and here are the 4 columns of data, and I click next and then finish. So when I go to next, it gives you that these are the variables that you can import. So maybe I don't want these, I just want the data. I don't want the header and stuff like that. So I can deselect them and then say import. So it creates that array, okay, 2-dimensional array, which contains those 4 columns. Then I go through the same process. So I take this and create a variable and label this as key, and then create the next one. Okay, and then I can plot one against the other just to see how linear it is. Is the data saturation temperature versus pressure linear over the entire range? Okay, so let's just plot that. I guess I had the wrong axes. I need to switch temperature and pressure. Okay, I switch that and then I plot that. So on the y-axis I have the saturation pressure, on the x-axis I have the temperature. You know that water freezes at 0 degrees, so the data starts at 0 degrees, and the highest data point is somewhere around 360, 370. What do you think that would correspond to?
Change of state. Change of state.
There would be change of state across this interface at all those temperatures and pressures. But at that point, the special point, critical point, at which point the distinction between the vapor and the liquid will cease. Okay? There's only one dense phase. Okay? So the data doesn't extend beyond that. So this is the entire range of data where liquid water can exist by itself. And it's clearly not linear. Okay, so I cannot put a first degree or second degree or third degree polynomial. So how do I go about fitting this? Okay. I have the data. So to start the curve fitting process, you use this function called CF tool. This is a graphical user interface for doing any curve fitting problem, linear or nonlinear. Okay, so it opens a GUI, and these are organized in the left to right, the order in which you should do the operations. First, import the data. So when you select import data, it says, okay, what is your X data? I have temperature. And what is Y data? I have pressure. Okay, so create a data set, pressure versus temperature, and you have imported the data. That's how the data looks. Okay, these are the data points. And the next step is fitting. Okay, so you select that, and you create a new fit. So here it tells you what kind of fit you want to do. Is it a linear fit, quadratic fit, cubic fit? You can select any one of them and then see how the fit looks. For example, apply a linear one. Obviously, it's a very bad, even for interpolation, it's a very bad representation. But it tells you all the statistics. So this is really the algorithms in CF tool is the same algorithm that we have seen, but it has more information in terms of, this is the polynomial, P1x plus P2. P1 is 48.68, the coefficient. P2 is minus 4593. But it has some statistics, goodness of fit, R square, which is, the R square should be close to 1 if it is a good fit, and the root mean square error, this is very large error, that should be as close to 0 as possible for a good fit. So it tells you, of course we can visually see that it is a very bad fit, but even when it is very close, visually it looks good, you can get quantitative information about the fit is good or not from this. So we abandon that and go back and say do a cubic fit and apply immediately. Let's do that. Is that a good fit? It looks really, it's much better than previous one, but there is an inflection point here, right? The error here is not as good, but R square is very close to 1, 0.9992, and the root mean square error is 188. Okay, now if you go for the 4th degree polynomial, R square is 1 and the root mean square error is 25. So that is a fairly good fit. Okay, you can do a lot of, without any programming, you can solve problems, right? And there is plotting and there is analysis. What would analysis do? Let's figure it out. So analyze the fit simply means you can evaluate that data at any range that you want. Here it goes from 0 to 374.4. That is the last data point. I don't know whether you guys in the back can see this. That gives you the range of x values, in our case temperature, over which you want to evaluate the fitted polynomial. Okay, and you can change any of these. It's a MATLAB syntax, so I can make it as 10, for example. That is 0 in steps of 10, go all the way up to 400. That would be a mistake because that extrapolation doesn't make sense. The water doesn't exist at those temperatures. And evaluate the fit. Okay. Apply. So it tells you these are the questions. Yeah.
So MATLAB automatically doesn't extrapolate.
Yeah. By default, they have set the range over which you want to evaluate to the minimum and maximum. So by default, it doesn't extrapolate, but you can force it to extrapolate by putting anything that you want there. Okay. So all you are identifying here is the range of independent variable over which you want to evaluate the fitted function. Okay, and then it tells you these are the values. Obviously, you can see this is not a very good fit. There are some negative pressures there. Even though it looks good here, okay, the red line gives you some negative values here. Okay, so physically it doesn't make sense. So it is not still a very good fit. What is a very good fit? I was going to show you that by going to the website. Let me try. Because in the website you will find an expression. Have you seen Antoine equation for vapor pressure? Okay, so that functional form gives you a better fit of vapor pressure data. This is nothing but vapor pressure data for steam. Okay, so they have an expression, and the nice thing about this curve fit tool is you can throw in any nonlinear expression. What we did was we just selected from the pull down menu, and we'll go back and put that particular expression, if I can find what that is. Any questions so far? Okay, so the curve fit tool allows you to fit any nonlinear function to any data and then analyze it by evaluating that at any particular position, generate graphs and things like that. So let me close that. And of course, generate code. Okay, I should show you that. So you can say generate code. What does this do? It creates a function called create fit between two data points T and P. So every process that you have gone through so far can be applied to a different data set using that function. So this function does the polynomial curve fitting using the choices that you have made. Okay, so that is a program that MATLAB generates for doing this job. Okay, so did I get my internet connection back? Just give me 1 minute. I want to show you the functional form from this website, and then see how we can explicitly specify such functional forms. Any questions? Okay, so here is the data that I took. The steam table data came from this source, Wikipedia. And there is an expression for you. Log P to the base 10 is equal to A minus B divided by T minus C. That form will fit the data most accurately. Okay? And they in fact tell you cannot use the entire range to fit that particular expression, so they've broken it up into two parts. From 273 to 333, the best value for the coefficients are A should be 7.23, B should be 1750, and C should be 38.1. Okay? And then you do it separately from 333 to 423. So you do it in sections, and that functional form will give you a much more accurate representation than what we have done with cubic or quartic polynomial. So we need to take this information and put it into CF2. If you learn that, then you can basically do any type of functional curve fitting. But here A, B, and C are the unknown coefficients. Okay, just like A1, A2, A3 in a polynomial curve fit. Okay, so is this a linear problem or a nonlinear curve fitting problem? Nonlinear. Why? Because you have A is linear, B is linear, but you have 1 over T minus C. The unknowns are A, B, and C. And as you said, there is a log term. So actually, P is equal to 10 to the power, that expression. So the whole thing is a nonlinear term. So how do I create such a function in curve fit 2? Okay, so I go to fitting, and I create a new fit, and type of fit. Okay, so here you can select different types of curve fits: Gaussian, interpolant, polynomial, which is what we used, power, but more importantly is custom equation. So I can put in any equation that I want there. I have to identify what are the coefficients. Then the CF tool will do a nonlinear optimization to minimize the sum of squares errors to find the best value for those expressions. So all I need to do is click new. Okay. So I need to identify the independent variable is x and the dependent variable is y, and the expression that I want to put no, I think I guess I picked the wrong one, right? Custom equation. General equation. Okay, not a linear equation, but a general equation. So I can throw any expression I want here. Okay. So what should I put here so that I capture the particular equation that I have shown? 10 to the power a minus b over t minus c. Okay. So 10 to the power a minus b divided by x minus c. So you see the formula appearing in the box. 10 to the power a minus b divided by x minus c, because I identify the independent variable as x and the dependent variable as y. Okay? So it will now thank you. Still not a valid expression. You guys know better than I do. Okay. So it automatically knows what are the variables for A, B, and C, and it gives you what it thinks is the best value. Now, did it really do the job? We need to go and look at the plot. Because we're running out of time. That's a terrible plot. That is the fit to. The blue line that you see is for that expression. Okay? These are the important things that you need to learn. Whether you're dealing with HISIS or MATLAB, when things don't work, why don't they work? Yeah.
Did you say the y axis is b? Did you look at the y?
No, I'm saying the data set here is p versus t. So it's going to take the data set from the variable p versus t, and the expression that I'm creating, I'm identifying y as the independent variable, x as the dependent variable.
So it doesn't matter, you have to put like b.
No, you don't have to do that. So y as a function of x is fine. It's just that the initial guesses that you have for a, b, and c are really very bad. So it found a local optimum, a local minimum in minimizing the error between the predicted value and the experimental value. I think I'm losing the attention, so it's probably not worth continuing beyond. I'll pick this up because I want to drive home a point here. Okay, so we'll do that in the next class. Yeah.
For the assignment, when you said generate a table, is it okay if we just wrote it out? Yeah, I just wrote it on. Sorry, I just wrote it on.
That's fine. That's fine.
What lectures is the quiz Thursday on? What lectures is the quiz Thursday focused on?
All the beginning.
Did you get it?
Is that's old, right?
This is the new one.
Oh, that's the new one.
Homework?
Yeah.
Okay. I need to close these. I've been losing while closing, so let me see whether I got the recording. I have a class.